today we are diving deep into one of the most fundamental, most powerful, and let's be honest, just downright weird particles in the entire universe. So, let's just start with a quick question. Think about it for a second. The raw power of a thunderstorm, the glowing screen that you're probably holding in your hand, and the very chemical processes that are keeping you alive right now. They seem like they're from completely different worlds, right? But believe it or not, they're all run by the exact same tiny, invisible force. You see it in the raw, untamed energy of a lightning bolt. That's just trillions upon trillions of electrons making a sudden, violent leap from the clouds to the ground, literally tearing through the sky. And then you have the complete opposite. It's the silent, perfectly controlled flow of those same particles that are lighting up the pixels on the screen you're looking at this very second. It's what's making this whole thing possible. And maybe most incredibly, it's the fundamental glue holding the molecules of your own body together. It's literally the architect of you, of me, of matter itself.
So, the answer connecting all this? It's a single, mind-bogglingly small particle, the electron. It is a fundamental piece of our reality, and if you want to understand how pretty much anything works, you've got to understand the electron. But that leads to the big question, right? How in the world do you discover something you can't see? Something that's part of everything but is completely invisible to us? Well, the story plays out like this amazing scientific detective mystery that took decades to finally crack.
You know, this wasn't one of those single eureka moments. Not at all. It was a slow burn, a puzzle that brilliant minds were piecing together for almost 60 years. It really just started as a hunch back in 1838. This idea that maybe, just maybe, electricity comes in these tiny, indivisible packets. It took decades before G. Johnston Stoney even gave it a name, Electron, in 1891. And even then, it was still just a cool theory, until a guy named J.J. Thomson finally proved it was real. Yeah, J.J. Thomson delivered the final piece of the puzzle. He was using something called a cathode ray tube. You can kind of think of it like a super early ancestor of an old tube TV. And he proved that these rays everyone was talking about weren't rays or waves at all. Nope, they were streams of actual, tiny, negatively charged particles. And here's the kicker. He realized they were identical no matter what material he used. They weren't just a part of some things, they were a universal ingredient of everything. And this is the part that just completely stunned the scientific world at the time. Its mass. Thomson figured out the electron was about 1/1836th the mass of a hydrogen atom, which was the lightest thing they knew. This wasn't just chipping a piece off an atom, it was finding a subatomic particle that was almost weightless. Okay, so we found this incredibly tiny particle. What's its day job? What does it actually do? Well, it turns out the electron is one of the busiest and frankly most important workers in the entire universe. So, inside every single atom, you've got these negative electrons that are held in place because they're attracted to the positive nucleus in the center. But here's the thing. They aren't orbiting like little planets, which is what we always see in diagrams. It's more like they exist in these blurry clouds of probability called orbitals, and the specific way those orbitals are arranged is what gives an element its unique identity. It's why gold is gold and oxygen is oxygen. And that arrangement, that's the key to all of chemistry. The electrons in the outer shells are what allow atoms to connect with each other, to form chemical bonds. Sometimes, one atom will just give an electron away to another. That's what happens in table salt. Other times, atoms will get together and share electrons to make stable molecules, like in water. It's this beautiful little dance of electrons that creates every single substance you've ever seen or touched. And this electron dance is what powers our entire world. See, in materials like copper wire, those outer electrons aren't really tied to any single atom. They form this kind of free-flowing sea of electrons. So when you apply a voltage, say from a battery, you're just giving that sea a little push, and all those electrons start flowing in one direction. That flow is electrical current. It's the simple principle behind every single wire, microchip, and power plant on the planet. Okay, so we've got a handle on this, right? It builds atoms, it powers our technology. Seems pretty straightforward. But, and this is a huge but, when we zoom in and look at the electron's true nature, the story takes a sharp turn into the truly bizarre world of quantum mechanics. It is so much stranger than anyone ever could have guessed. This right here is the central mystery of the quantum world. When we actually try to look at an electron, what are we seeing? Is it a thing, or is it something else? The unbelievable answer is, well, it depends on how you look at it.
Experiments have shown us that the electron is essentially living a double life. Sometimes it acts just like you'd expect, like a tiny, solid billiard ball.
It has a specific location, it can bounce off of things, but other times it behaves just like a wave in the ocean. It spreads out, it can interfere with itself, it can literally be in multiple places at the exact same time. We call it wave-particle duality, and it's a fundamental, measured reality of our universe.
And as if that wasn't weird enough, electrons are also fiercely individualistic. They follow this fundamental rule called the Pauli exclusion principle. You can basically think of it as nature's ultimate social distancing law. It says that no two electrons can ever be in the exact same quantum state at the same time. This antisocial behavior is what forces them to stack up in different energy levels around a nucleus, building the structure of atoms layer by layer.
So get this. The crucial takeaway here is that the solidity of the world around us is kind of a quantum illusion. The only reason your hand doesn't just pass straight through the desk in front of you is because the electrons in your hand are fundamentally repelling the electrons in the desk. Thanks to this exclusion principle, they refuse to share the same space. The world feels solid because electrons are standoffish.
And that really just leaves us with this one last, truly mind-bending thought to chew on. If the fundamental building block of our solid, predictable world is this uncertain, ghostly thing that's both a particle and a wave, that only really exists in a haze of probability until we look at it, what does that actually say about the nature of reality itself?